So, now let us try to quantify the number of trapped charges. Okay. So, it is not only the qualitative understanding of the disordered semiconductor that is important, but also the methods and means to quantify these estimates. And from this point on, we will study a lot of the methods and tools used to quantify and calculate carrier concentrations and therefore the currents in disordered semiconductor based devices. But since the mathematics can get quite involved, please keep in mind that the focus is not to be on the mathematics, but on the general approach to solving these problems. So, to start with, the primary difference between crystalline materials and disordered materials is the states inside the gap, and therefore, the trapped carrier concentration inside the gap. Now, inside the gap, the trapped carrier concentration is simply the density of states into the Fermi function f of E. In the case of crystalline materials, this density of states was 0 and therefore, the trapped carrier concentration was 0, but in the case of disordered materials, this density of states has to be defined, and a key towards understanding the density of states, the key towards understanding the carrier concentration in disordered semiconductors is the definition of the density of states. So, in this on this page, let us just look at how one would go about in quantifying the density of states. So, this particular picture is taken from this reference, and it identifies the density of states picture for amorphous hydrogenated silicon. Okay. And such a picture can be developed for any disordered semiconductor. So, this is just being used as an example. So, in order to experimentally estimate the density of states, okay, one could perform different experiments such as the deep level transient spectroscopy, and one could get an experimental confirmation as to what the density of state distribution is with energy. Now, what is shown here is the acceptor like density of states in the case of this particular material, where this could be considered to be the Fermi level, and then you have the acceptor like deep states and you have the acceptor like tail states, and that is your conduction band edge. Now, how does one quantify, how does one model the density of states? A very common model is typically if you have a density of state distribution that looks like this, wherein the deep states, the logarithm of the density of states versus energy for the deep states is like a straight line, and the same holds true for the tail state distribution, with the exception being that the slopes are different. Okay. So, how does one go about modeling this? A good way to approach this is by defining the density of states to be exponentially dependent on the energy. So, we say that the density of states is some prefactor into the exponential of E minus EC divided by a fitting parameter which is called as the characteristic energy. So, here Tc, K is nothing but the Boltzmann's coefficient, and Tc is a parameter which is called as the characteristic temperature, or one could also use the equivalence which is the characteristic voltage, which is KTC by Q. So, this can also be called as a characteristic voltage. Now, using this fitting parameter Tc, one could define a characteristic energy that fits this definition, that fits the experimental data using this kind of a model. Now, this is a general expression, and therefore, you could have one characteristic temperature for the deep states and one characteristic temperature for the tail state. So, one could say that the density of states, so this is a very general expression. So, this is not this is only to define the approach to modeling. One could say that the density, the acceptor like density of acceptor like deep states have a relation which is say some GOD, which is some prefactor that needs to be estimated from the experimental data, into the exponential of E minus EC by a characteristic temperature for the deep states. And the acceptor like tail states is given by say GAT naught into exponential of E minus EC by KTT, which is the characteristic temperature for the tail states. And similarly one could define the donor like deep states and the donor like tail states based on the experimental data found. Okay, so the donor like states are not shown in this picture here. So this is the first step towards any modeling, which is to define the density of states, and we can define this using an exponential definition and with something called as a fitting parameter called as the characteristic temperature. So the next step is to calculate the total number of localized carriers. So what do you mean by localized carriers? These are carriers which are trapped and are sitting in the gap states. And how do we define the carrier concentration of localized carriers? It is simply all carriers that sit from the Fermi level to the conduction band edge. So here again we are looking at only the carriers sitting in the acceptor like states. Okay. So from EFO to EC, and that is nothing but the product of the Fermi function. So here you can see the Fermi function into the density of states. We had defined a density of states which has got a characteristic temperature and an exponential dependence on energy. So that is the density of states into the Fermi function, and this integral is performed with respect to dE from Fermi level to the conduction band edge. So which implies that we are integrating and calculating all the carriers that are present in this region here, which are our trapped carriers in the acceptor like states. Now this integral the mathematics here is quite involved, but do not focus on the mathematics. Depending on the what do you say, the characteristic temperature. Okay, so here I should define this particular parameter alpha. Okay. So this particular parameter alpha is nothing but the ratio of the characteristic temperature to the ambient temperature, and depending on what alpha is or what the value of alpha is, this integral can be, the answer to this integral can be different. Now it so happens that in this particular case, for this particular example, okay, if the alpha is greater than 1, which means if the characteristic temperature is greater than your ambient temperature, which so happens in the case of deep states, then the number of localized carriers in the deep states turns out to be this particular answer here. And on the other hand, if the alpha is less than 1, which happens to be the case in the case of tail states. So the characteristic temperature for the tail states is less than the ambient temperature, and therefore this integral, the same integral, turns out to be a very different, gives you a very different answer which looks like this. Okay. So as I mentioned, the mathematics is a bit involved, but I am trying to keep the focus on the approach. So now we can have a complete definition of the carrier concentrations. So here are the localized carriers. So there are two kinds of carriers in disordered materials. You have trapped carriers or localized carriers. So these are nothing but the trapped carriers which are trapped in the states in the gap. And you have the free carriers which are sitting in the extended states. So these are the carriers sitting in the extended states. So these are the ones that can provide that possess a large mobility and which can contribute to the current. So the number of free carriers per unit volume is given by an expression that you are all very familiar with, which is the density of effective density of states into e to the power EC minus EF minus VC minus EF by KT. So this expression is very similar from the compared to the case of crystalline silicon. But this is something new which did not exist in the case of crystalline silicon, which is the number of carriers that are trapped per unit volume is given by the total number of trapped carriers in the tail states plus the total number of trapped carriers in the deep states. And those answers are given here for this particular example. So here is a nice picture. So here is the charge per unit volume versus energy. So, you can see that the free carrier concentration goes like this, okay, and the trapped carrier concentration is shown here, where this is all due to the deep states and that is all due to the tail states. So, it is quite important to note that at thermal equilibrium it could so happen that the trapped carrier concentration is much larger than the free carrier concentration. So, having given that introduction to disordered semiconductors, let us now look at thin film transistors, and we will see we will look at the techniques used to model thin film transistors, which are basically the field effect transistors using disordered semiconductors and using a thin film process flow. So, as I mentioned before, the thin film transistor has got a thin film metallic gate, a thin film insulator, a thin film of semiconductor, and your source and drain contacts, which are tailored such that you have good carrier injection and therefore low contact resistance. Now, a key point to note is if you are building transistors out of many inorganic materials or many organic materials, the density of states largely determines the kind of thin film transistor. Okay, and what I mean by that is with regards to whether the transistor is N type, P type, or whether the process allows a complementary MOS device. Okay, and that has got to do with the density of states picture, and we will have a look at the working of the thin film transistor to understand this. Now, how does a thin film transistor work? Now, so what we have to look at here is the density of states picture. Okay, so let us say we have applied a gate voltage. We built a thin film transistor and we start throwing in positive charge on the gate. Now, in the case of crystalline silicon, what was the consequence of us putting positive charge on the gate? In the case of crystalline silicon, if we looked at the band gap was very free and the Fermi level was free to move about, or in other words the band bending was very free. So, in crystalline silicon we had a device structure wherein we had a doped semiconductor and we had a insulator and a gate, and the consequence of us adding positive charge was firstly we achieved flat band, and then if you use a P type silicon body, we saw that we first achieved depletion. We had our intrinsic Fermi level bend towards the Fermi level, or in other words the conduction band and valence band began to bend towards the Fermi level. We first achieved depletion wherein all the positive charge here was compensated by the negatively charged ions, acceptor like ions in the bulk. And then by adding more and more positive charge, we could achieve a significant amount of band bending. The band bending became very significant and the intrinsic Fermi level bent below the Fermi level near the interface, and therefore, the moment EF became greater than EI, we found that electrons began to appear at the interface and we had a region of operation called as the inversion region of operation, and these electrons were the ones that enabled carrier transport between source and drain. So, that was the working of the crystalline silicon semiconductor. Now, in the case of disordered semiconductors, the Fermi level is not free to move. There is band bending, but it strongly depends upon the density of states. Okay. Now, as we add positive charge on the gate of a non-crystalline semiconductor MOSFET, or in other words a thin film transistor, is that the Fermi level tries to start moving towards the conduction band edge. Okay. In other words, if you think of the band bending picture, the conduction band attempts to bend towards the Fermi level. But since there are so many states sitting in the band gap, the movement of the Fermi level towards the conduction band implies that these states must now be filled with electrons before the Fermi level can make progress and move towards the conduction band edge. Or in other words, all the positive charge that we are applying on the gate is being compensated by the trapped charge that is appearing in the gap states as the Fermi level makes its move towards the conduction band edge. So, let us say this is the, let us say that figure 1 is the position where your VGS is equal to flat band. So, all bands are flat at this point. Now, as we add more and more positive charge on the gate, we find that the Fermi level starts moving towards the conduction band edge, or in other words the conduction band tries to start bending towards the Fermi level. But since the Fermi level is now climbed up by this distance as compared to its flat band point, all these states are now filled with carriers, okay, they are all filled with electrons, and that occupancy depends upon the product of the Fermi function and the density of states. Now, it is these electrons that are going to compensate for the positive charge that we have applied on the gate. In the case of crystalline silicon, we found that it was the band bending and it was the exposed dopant ions that was contributing or compensating for the positive charge on the gate. But here it is the trapped charge or these electrons that are occupying acceptor like states that are going to contribute to the charge balance. So, now the meaning of acceptor like states becomes very clear, right. So, as the Fermi level moves up, these states were filled with electrons and therefore, they all became negatively charged. So, they are playing the same role as the doped acceptor like ions in the case of an N channel MOSFET. Okay. So, as the Fermi level moves up, the acceptor like states get filled with electrons and this charge compensates for the charge on the gate. So, as more and more positive charge is applied on the gate, the Fermi level starts heading closer and closer to the conduction band edge, and at some point there will be enough free carriers sitting in the conduction band edge, above the conduction band edge in the extended states to permit significant current. Okay. And this point is defined as your threshold voltage. Okay. So, look at the clear difference between the operation of a MOSFET and that of a TFT. So, let us spend some time looking at this difference. In the case of crystalline MOSFETs, what defined our threshold voltage? What was the threshold voltage? In the case of crystalline silicon MOSFETs, we had a gate and we had an insulator, and when we drew the band bending diagram, since the band gap was very clean, the conduction band could move towards the Fermi level very freely. So, at first we had to achieve flat band, that was the first milestone, and then so that was the, let us say that is the intrinsic Fermi level and that was the Fermi level of the p type doped semiconductor. So, first we achieved flat band, but then as we started adding more and more positive charge, the Fermi level moved closer to the conduction band, or in other words there was some band bending, and all the positive charge in the gate was compensated for by the depletion charge in the semiconductor. So, the next milestone towards achieving flat threshold voltage was that we needed to deplete the semiconductor enough in order to get the bands to bend significantly. And finally, we had to achieve inversion, and how was the inversion point defined? It was that point at which the band bending was so significant that the electron concentration at the interface managed to match the hole concentration in the bulk. So, we said that this was equal to phi f, and therefore, the surface potential had to be 2 phi f in order to achieve threshold voltage. So, this had to become 2 phi f, and at this point we said that there is enough inversion charge that we considered the MOSFET to be working above threshold voltage. So, that was our definition of threshold voltage. What about non-crystalline semiconductors, amorphous semiconductors? In this case, there is nothing like a depletion layer. The semiconductor is intrinsic, there is nothing like a depletion layer. There is nothing like achieving this 2 phi f. So, all this there is no inversion point wherein the surface potential achieves 2 phi f. So, these definitions do not exist in a similar manner as in the case of crystalline semiconductors. Instead what we have is we have a conduction band, we have states inside the band gap, and let us say this is the Fermi level at flat band. So, yes, you do have flat band. So, we have the first milestone to cross is the flat band, but threshold voltage is defined as that voltage wherein the Fermi level gets close enough to the conduction band edge, so that all the states above the conduction band edge, the extended states, are populated with some amount of free carriers that enable a measurable level of conduction. So, that is the definition of threshold voltage, which is a very vague definition, because it depends upon your density of states profile. So, the density of state distribution is very large, you need to trap a lot more carriers before the Fermi level can climb till that point, and therefore, your threshold voltage is going to be much larger. Okay. And therefore, the threshold voltage, the proper definition of threshold voltage. So, let us say that this is the location of the Fermi level when the carriers, when there is significant carrier population in the extended states. So, the definition of threshold voltage is that the Fermi level needs to climb up and past these gaps, past all these states, which implies that all these states first need to be filled with electrons, and therefore, all this negative charge will balance all the positive charge applied on the gate, and therefore, the definition of threshold voltage is the flat band voltage plus this total trapped charge in all these states divided by Cox. So, how much of charge do we need to trap in all these states so as to get the Fermi level close enough to the conduction band edge, so as to get enough carriers in the extended states. So, that is the definition of threshold voltage, and this depends upon the density of states picture. So, we can see how the density of states is controlling the operation of the MOSFET. Now, there is another point. Let us look at the mobility of carriers. So, in the conduction band states, okay, so let us look at the transients, let us look at the transients. Now, as the Fermi level moves through these states, okay, we have something called as a subthreshold operation. So, here was the flat band voltage. So, this was the flat band voltage, and between this point to that point we have subthreshold operation. So, in subthreshold mode of operation, the Fermi level sits mostly in the deep states. It is only when you are close to threshold voltage that the Fermi level has climbed far enough that it has gone into tail states. So, in subthreshold operation, the Fermi level sits in the deep states, but then as the Fermi level makes its climb, the speed at which it makes its climb towards the conduction band depends upon the density of states here. So, let us say that there are a large number of states to be filled. The Fermi level will climb very slowly, because it needs to fill all these states with electrons before it can move upward. But then if there are very few states to be filled, then the Fermi level can climb a little faster. So, so let us say that the Fermi level, let us say that the density of states looks like this. The Fermi level is climbing through very slowly because there are a large number of states, and then it increases its speed, and then it goes up very quickly through this region because there are very few states, and then it becomes slow again because there are a large number of states again. So, this implies that the threshold slope or the subthreshold swing would reflect this behavior. You will find that the current is growing very slowly because the Fermi level is moving very slowly through the gap states, and then in this region, as the Fermi level begins to move quickly, you will find that the current also increases rapidly, and once the Fermi level enters these states, you will find the current increases slowly, and then the MOSFET enters above threshold operation. So, in some sense, the subthreshold slope and the subthreshold swing are all dependent on the nature of the density of the deep states. So, that is the second difference. So, therefore, in the case of crystalline silicon, we found that the subthreshold slope, if we looked at the subthreshold slope, it depended on something called as 1 plus C depletion by C ox, and because we had interfacial trap charge you have C interfacial. But here one can define the subthreshold slope as 1 plus C interfacial plus C gap states by C ox. The third point to note has got to do with the mobility of carriers. So, why did we say that the amorphous silicon semiconductor has more n type behavior as compared to p type behavior, and the answer to that also lies in the density of states diagram. So, let us say we have two options. We have the Fermi level sitting here at flat band, and we would, by applying positive voltage, like to move the Fermi level closer to the conduction band edge, or as compared to moving the, and by applying negative voltage we would like to move the Fermi level closer to the valence band edge. Now, let us see which of these is more feasible. Now, it so happens in amorphous silicon that the density of states in the valence band, or the valence band, or the donor like tail states, has got a much larger density as compared to the acceptor like tail states. So, you can see that this slope here is very sharp, whereas this slope here is very large. Now, because of this asymmetry, you have a very different it has got a very direct consequence on the practicality of having hole type transport or electron like transport. So, in order to create holes, in order to allow holes to transport, be the carriers of current transport, we need the Fermi level to move towards the valence band edge. But this, because of the large density of states, this can happen only at very large negative voltages. On the other hand, it is much easier to get the Fermi level closer to the conduction band edge because of the smaller density of states in the tail states. Okay. So, the presence of gap states determines firstly the threshold voltage, secondly the subthreshold slope, and thirdly the type of transport, is it an n type or a p type transport. Okay. And this is the significant difference between disordered semiconductor based MOSFETs, which are called as thin film transistors, and the crystalline semiconductor based MOSFETs. So, let us now look at let us use all this information to try and see the methods to develop analytical models for thin film transistors. So, again here the mathematics might be very involved, but the focus should be on the approach as compared to the details of the derivations. So, the first step is, let us look at the MIS electrostatics, which is equivalent to your MOS capacitor, the electrostatics of the MOS structure. So, the first step is to write down Poisson's equation. In the case of your crystalline silicon MOSFETs, we found that Poisson's equation was if you write it in terms of the electric field, it was given by d by dx is q Na by epsilon s, okay, where Na was the acceptor ion concentration in the p type bulk which we had used to develop our MOSFET. And in terms of the potential, it was d square phi by dx square is q Na by epsilon s. Now, in the case of amorphous semiconductors, what determines the Poisson's equation? So, what determines the charge carriers? Okay. So, this charge carrier concentration is given by the trapped charge. So, what constitutes all these charge carriers? It is the trapped charge plus the free charge. So, if you go back to this general picture of which where we looked at the movement of the Fermi level through the gap states, we saw that all these trapped charges were the ones that were responding to the applied electric field or the applied gate voltage, and we also had some amount of free carriers depending upon the location of the Fermi level. So, any electrostatics with regards to the band bending or to identify the electric fields inside the semiconductor must must consider the trapped charge concentration and this free carrier concentration. So, therefore, we now have a Poisson's equation which has got a free carrier concentration, which has got a trapped carrier concentration, and this is the trapped carrier in the tail states and the trapped carriers in the deep states. So, you have 3 terms, which is the free carrier sitting above the conduction bandage, the trapped carriers in the tail states and the trapped carriers in the deep states. Now, each one of these terms depends upon the potential that is applied. So, therefore, this is a Poisson's equation which will also have the potential term on the right hand side, and all of you are familiar as to the means to solve this particular equation. But the free carrier concentration will have an e to the power phi by phi th term, where this is the thermal voltage. The trapped carrier concentration in the tail states will have an e to the power phi by phi t term, where this is the characteristic voltage of the tail state trapped charge, and the deep trapped charge carrier concentration will have an e to the power phi by phi d term, where phi d is the deep state characteristic voltage. So, using these 3 terms, one can write out Poisson's equation and solve it in all its detail. But for the purpose of these slides, what we have done here is we have merged all 3 exponentials and defined an effective carrier concentration and an effective characteristic voltage, and written the sum of these 3 terms as simply this particular exponential. Okay, so, this need not be, this is definitely not the most accurate approach, but it is being done only for the purpose of this example here. So, what does this mean? It says that if the trapped carrier concentration is the largest, if say one of these two is the largest, then NEO, this term will contain of mostly trapped carriers, and this characteristic voltage will tend towards one of these characteristic voltages. On the other hand, if this term here has got mostly free carriers, then NEO will tend towards this particular concentration, that is the concentration of NFO, and this term here will tend towards phi th. Okay, so, that is the implication of having this exponential. Now, all that is left is for us to solve this particular exponential, and here are the details of all the solution. So, we have this Poisson's equation to be solved, and there are 2 boundary conditions. The first boundary condition says that so when you have band bending in the semiconductor, the point at which phi is 0, that is when we achieve flat band, we have defined phi the reference potential as the potential in the bulk. So, when phi is 0, you have a 0 electric field, that is when the bands become flat, the electric field is 0. The second boundary condition has got to do with the interface, and what we say there is that the electric displacement, which is the permittivity into the electric field at x equal to 0, is given by Ci into Vgs minus Vfp minus the surface potential. So, that is the second boundary condition. So, by applying these 2 boundary conditions and going through all this mathematics, we will find that this is the expression for the electric field, and going through all this mathematics by applying both the boundary conditions, we find that the surface potential is defined in terms of a Lambert W function, okay, which can be approximated as this particular expression here. And the surface potential therefore is and the potential through the semiconductor, not the surface potential, the potential through the semiconductor is given by this particular expression. The surface potential in particular is the potential at x equal to 0. Now, the next step towards modeling is, now we have the potential function and we have the surface potential. Now, the surface potential determines the free carrier concentration per unit volume, because the free carrier concentration per unit volume is defined by this particular expression here, which is your NFO into e to the power phi by phi th. But the surface potential defines the free carrier concentration per unit volume near the surface. But however, for the definition of your current densities, okay, it is useful to define the free carrier concentration per unit area, and the way this is done is by integrating NF in thickness, and you integrate it from 0 through the thickness of the semiconductor. So, the point is thin film transistors are made up of thin film semiconductors, and this and what we are saying here is that NF is the free carrier concentration through the entire thickness of the semiconductor, and by performing this integral we identify the free carrier concentration per unit area. So, that integral is solved out here in full detail, and we find that the free carrier concentration per unit area is given by this particular expression here. And you see two parameters that did not appear in the case of crystalline silicon MOSFETs. In the case of crystalline silicon MOSFETs, the free carrier concentration per unit area was simply Cox into VGS minus VT minus VC. Okay. But here you have two other parameters, you have an exponent which is called alpha minus 1, and you have a prefactor which is called as gamma. So, what are alpha and gamma? Alpha is your twice your effective, is 2 times the effective voltage divided by your phi th. In other words, your alpha is nothing but the term that we defined earlier, which is your twice your characteristic temperature divided by the ambient temperature. And in the case of crystalline semiconductor materials, this characteristic temperature was the same as the ambient temperature, or in other words phi E was known to be the same as phi th, and therefore alpha was the same as 2, and therefore this term here became 2 minus 1, which was 1. So, therefore, crystalline silicon MOSFETs did not have any factor there, but this is the more general version of the semiconductor, and you find that alpha is twice Tc by T. So, that is your parameter alpha that depends upon the characteristic temperature of the gap states. And what is gamma? Gamma is defined by this particular term. The key point here is that gamma defines the number of carriers in the free states divided by the total effective number of carriers, which in some sense includes the carriers in the trap states plus the carriers in the free states. Therefore, gamma is an indicator of this ratio of the free state carrier concentration by the total carrier concentration. And using this particular this particular relation, which is the number of carriers per unit area, in order to define your current voltage characteristics, we find that the current voltage characteristics is given by this expression, which can then be integrated to define the current voltage characteristics of your TFT. Okay. So, in the case of MOSFETs, alpha was simply 2, and we ended up with this particular relation. But even in the case of TFTs, if these particular assumptions are made, then you will find that the current voltage characteristics of a TFT is quite similar to the current voltage characteristics of a MOSFET. So, in some sense this is a summary of how one goes about with regards to deriving the current voltage characteristics of a TFT. Now, as we saw, this term threshold voltage in the TFT is given by the total trap charge concentration by Cox plus the flat band voltage. And this plot here shows the typical current transfer and output characteristics for a TFT. Now, since the threshold voltage is nothing but the trap charge by Cox plus VFB, this is the trap charge per unit area divided by Cox plus VFB, the threshold voltage ends up being a very dynamic quantity. Okay, and one sees a very unique phenomena in disordered semiconductors, which is something called as a threshold voltage shift. Okay. So, what does this mean? So, in the case of crystalline silicon MOSFETs, the threshold voltage was more or less a fixed quantity. I mean, once you know the threshold voltage of the MOSFET, you used it for modeling your circuit behavior. But in the case of disordered semiconductors, when the thin film transistor is in operation, so let us say you apply a certain gate to source voltage and you apply a certain drain to source voltage, then when this thin film transistor is in operation, you find that the threshold voltage in a thin film transistor becomes a function of time. In other words, as the MOSFET is driving current, the current in the MOSFET begins to decrease in time. Okay. Why does this happen? So, this is a very key phenomena which is very peculiar to disordered semiconductors. Now, there are two mechanisms, okay, which result in this threshold voltage shift. The first mechanism can be said to be both these mechanisms are related to charge trapping, but the first mechanism is charge trapping in the dielectric and in interfacial states. So, although it is not written here, you can say it is dielectric and interfacial states, that is at the semiconductor insulator interface. Okay. So, these two are the first parameters or mechanisms that contribute to charge trapping. There is another mechanism which contributes to charge trapping, and that is related to something called as defect state creation. So, what is defect state creation? So, we saw that there was a certain density of states in the semiconductor. So, that was the energy and this was the density of states. Now, it so happens that as the MOSFET is in operation, so you have your Fermi level here, the MOSFET is in operation or the TFT is in operation. So, what happens is that due to the disorder in the semiconductor and due to electrons interacting with these weak and dangling bonds, stronger defects are created. In other words, new states are created deep inside the band gap. Okay. So, the presence of these new states results in all the free electrons now getting trapped in these states, or in other words, it appears like as though the Fermi level is slipping down in energies, even though we have a large gate voltage. And this movement of the Fermi level down in energy simply because of the creation of defect states results in it appearing like as though the threshold voltage of the transistor is increasing with time. So, it is a very dynamic phenomena, and one finds the threshold voltage of the transistor increases with time and is given by a relation that looks like this. Okay, it is something called as a stretched exponential function, and that experiments show this, which is if you apply a certain gate voltage and if the gate voltage is larger, the rapidity with which the speed at which the threshold voltage increases will also be larger. Okay. So, this is a phenomena that is quite unique to disordered semiconductors and is of quite some importance.